So we need to find a way to sample on the surface. I don't want to write molecular dynamics because you have to deal with the velocities, and that's a big mess. So we're going to implement Markov chain Monte Carlo here. The thing is, we're not going to use it just for coordinate sampling. It's also a vital technique, a vital ingredient in actually doing enhanced sampling as well. Maybe it's the guacamole. It's really important. So we want a rule for flow between states that preserves the probability at the states. What do I mean? So in equations, this is what I mean. So here's the probability we're in state 1, and here's the probability we're in state I. Here's the probability we're in state J. Now, state is like literally anything. We're going to start out with the state being an X configuration. So the probability we're in X as Xi versus Xj. But as we'll see, we can use it more generally as well. And so what we want to have is make sure that this ratio is equal to this ratio, where T, this transition from J to I, is the chance of going from J to I over T of I, the chance of going from I to J, the chance of going from I to J. So the basic idea is we want to keep the ratio of stuff. You can think of like the probability as like some fluid. We want to keep the ratio of the stuff in state I and state J equal by making sure that the ratio of stuff going in and out is consistent with that. If there shouldn't be very much in I, then the flow should be mostly from I to J, not from J to I. There should not be nearly as much going from J back to I if I is less probable. So it's really like materials and energy balances here. We want to make sure that the probability of the stuff is equal to the flow in and out. The amount of stuff in I and J is consistent with the flow in out of I and J. And if you make sure that this is true for every single possible state, for all possible Xi's and Xj's, or if you have different containers, all possible containers, it's what's called detailed balance. Now, it turns out that you don't need to have detailed balance to get the Boltzmann distribution right. You could think of something where actually you're going from I to J, there's no flow, there's flow from I to J, but no flow back from J to I. You go from I to J, then from J to K, and from K back to I. And if you're very, very, very clever, you can figure out a way for that to work to get, and still get the Boltzmann distribution out. But detailed balance is the easiest way to do it. So there's some algorithms that are too clever by half and do something cleverer than detailed balance. But most algorithms depend on detailed balance. And so we're going to focus on this version right now, is making sure whatever we do to move between states, we satisfy these criteria. And if we do, then we will get the right probability distributions out in the end. So we're doing this with molecules, right? And so the probabilities of two configurations is going to be this ratio of probabilities, right? It's coming back again. Like this is the normalized probability. So this is the super important part. It's not a ratio of just potential energies. It's a ratio of the free energy over the potential energies. Now, in the case that you're dealing with two Xi and Xj that belong to the same state, the free energy corresponding to the state is all going to be the same. So that's going to cancel. So in this case, you will have just a this. Oops, that's in the wrong place. But we'll fix that later. But essentially, the potential energy difference between the two of them. So that's what you want to make sure. You want to make sure that your transition rule gives you this probability ratio. So any rule that satisfies this will work. So this probability ratio has to be equal to this transition ratio. Any rule of transition, by rule of transitions, I just mean like an algorithm. And A here is the free energy of the state, which is either Gibbs free energy or Helmholtz free energy. Thanks for asking for that clarification. That's the thing that turns the Boltzmann distribution from a proportional to the probability equals. That's the factor that makes it a true probability distribution. Can I elaborate how algorithms can break detailed balance and still maintain the right ensemble distribution? So detailed balance guarantees it gives you the right distribution. You can come up with rules, and some algorithms do, that break detailed balance and still maintain it. It gets very complicated because it ends up being much harder to prove that they're right. So I'm not going to get into that now because I have a hard time. I have to like dig out. It's like a specific proof for each different thing, since you have to come up with a different rule. Detailed balance, 90% of the algorithms use it, and it worked great. Yeah, don't break detailed. You only break detailed balance. These are professionals working on a closed course. They can break detailed balance. Don't break detailed balance at home. Yes, yes. You can. You just have to be you have to know what you're doing. You have to know what you're doing. Okay, so here's a rule. Step 1, propose a move randomly and isotropically in any direction. We'll talk about why it's important to be isotropic later. For isotropic, this means, for this case, it's up and down in the same direction for a simple thing. So first you propose a move randomly and isotropically in either direction. So it's like an equal chance to go up and down. And if the new energy is type of this. So that should be if u xj is less than u xi. It makes no sense. Of course, u xj is always equal to u xj. If u xj is less than u xi, then move there. So if your new energy is lower, go. Lower energy is good. Go do it. If your new energy is higher, then move with this probability that's equal to that ratio of probabilities. So that's the step 2. So this is called the Metropolis algorithm. Actually, Metropolis just gave the computer power for the scientist doing it. Do physical systems ever break detailed balance and equilibrium? Not if they're following Newton's laws, and I think quantum might. Ooh, that's a good question. Classical systems do not, like Newton's laws of motion, obey detailed balance. Maybe some quantum systems do, but not on average. Like a macroscopic average is no. So I'll have to think about that a little bit more, but Newton's equations of motion do not. But remember, we can do something different. We're on computer. We can break those laws as long as we keep we can break any law we want to, as long as we obey the ones that are necessary for physical mechanics. Okay, Metropolis algorithm was actually invented by a husband and wife team working closely together, Marshall and Ariana Rosenbluth, in 1951. Ariana Rosenbluth actually died of COVID 2 years ago. So we're at the point where just barely passing out of the generation that these were developed. So they worked on this together as a young couple, but Metropolis, for whatever reason, ended up as the first name on the paper. Okay, so yeah, so let's check to make sure this is valid. So propose a move randomly and isotropically in any direction. Again, I'm going over this. You've probably seen this before, but because the same algorithm is used for some of the enhanced sampling tricks as well. Okay. So this is really important because otherwise the change of proposing a move from I to j is not the same as the reverse. So it turns out the transition probability, the chance of going from I to j, is a product of two things: a chance of proposing a move from I to j, and then a chance of accepting that move. You'll see this if you start looking at like Metropolis says, find a copy. That's a good question. So I will post the slides after. I apologize. You won't be able to write in the slides, we'll write in the lecture, but these will be posted later this afternoon. Thanks for the question. Yeah, chance of proposing times the chance of accepting. So if you make sure your chance of proposing is isotropic, it's the same. Your chance of going up your chance of looking from I going up and your chance of looking from j going down, as long as they're the same, then we can just cancel this out and not worry about it. Again, if you're a professional, you can use the Metropolis Hastings and use a non-isotropic proposal distribution, but then you have to account for it in your acceptance ratio. So if we look at the ratio of these, if we assume it's isotropic, these cancel out and we just get the ratio of accepting that. So what's our acceptance ratio? So we're using an isotropic mood, so these cancels out. This is going to be equal to, okay, if uij is less than ux, so those are our two choices for each, right? It's either greater than or less than. If it's equal, then we can pretend to say we can equal. It turns out that the formulas give the same answer if they're equal. So we're going from j to I. Notice here, this is j to I. So if we're dealing with j to I, if essentially we've got the reverse direction on top. If uxi is less than uxj, it's a lower energy. We move, great. If it's higher, then we use this formula, right? uxi, where we're moving to minus where we're going from. So that equals, great. If it's less, that equals the right exactly what we're looking for. Now, in the other direction, if uxi is greater than uxj, oh, here we're actually moving from I to j. So in this case, if it's greater, we're moving to j. This will be 1 here, because moving from I to j, xj is lower than xi, it's 1. And if it's the other direction, then we use this the formula. It's where we're going to minus where we're going from. So notice here, when we divide this, it's 1 over this. So there's an extra minus sign. So it's j minus I. And here, there's no minus sign. It's just this divided by 1. They're equal to the same thing. And that's the check. So you'll probably, this is a slide where you probably will have to go over the slide afterwards and just make sure it works out. But whether it's above or below, they both cancel. You either have 1 over the thing, or you have the thing. And so you get the right answer in both cases. Whether the energy is greater than or less than, it gives the right answer. Now, you can, I means the old, so that's a great question. I means the old and J means the new. Depends. On the numerator, J is the old and I is the new. In the denominator, I is the old and J is the new. The arrow tells you which one. The arrow tells you where you're going. So it's from on this. So the thing is, these are not hard. It's not hard math. It's confusing math, because you got to keep your labels and your arrows right. It's not hard, but it is confusing. You got to be careful. Okay, so check. Now, it turns out there's other rules as well. Metropolis is not the only rule. There's Barker rule. There's a bunch of others. Metropolis ends up being better than most and pretty easy. So we do that. So yeah, that's the step 2. Okay, so back to the notebook. Let's actually code this up. And new share. We're back to the notebook. Okay, so we're going to code it up. So here's my Monte Carlo step in 1D. I do a random normal, so I'm going to do a Gaussian. It doesn't have to be Gaussian, but you do want a function that's symmetric so that your chances of going up and down are the same. And 1 unit, I mean, the sigma is about 1 unit, so it takes like 2 or 3 steps to get out. That seems like a reasonable step to take. It means that the potential is changing relatively gradually. So our new step is the old plus the new step. So we have to reevaluate the energies because we're going to need those. So if new P is lower than old P, great. That's our new configuration. If it's higher, if it's higher, then we have to compute. And, you know, you'll have to go through whenever I write this up, I like make a sign error the first time. So I have to check it again. So this is the formula, we plug it in. X new, so it's, you have some, if it's a big difference, you have a small chance of changing. If it's a small chance, you've got a moderate chance of changing. And so these are the two. If not, we go to the next step. So in Monte Carlo, sometimes the next step is the same step. You just like stay in the same place multiple times. So you don't just increment your step whenever it changes. To get the averages right, you have to stay there sometimes. So if it's too high, if it's way too high, you're never going to change. You're just going to stay there for a bit. So that's our thing. Okay, now let's simulate our system. 10,000 steps is easy with this. 5 is a good temperature to set. Let's run. We set our initial position. It's an incremental algorithm. We have to start somewhere, and let's go. Poof. Okay. So that looks, it's jiggling around. It moving. That's great. Let's look at a histogram of where it is. Okay, that's fine. Let's calculate the average energy. So here I'm just evaluating. I take my trajectory and evaluate the energies. There's the mean. Do you remember what the mean was supposed to be with x equals 5? Let's go up. So temperature equals 5. It's, I have it here, 1. So that's a little high. Why is that? Why do you think the average is high? Well, remember, the probability distribution at temperature of 5 should be, it should be over here, I don't know, 2/3 of the time, maybe? But it never gets there, right? It's just in the first minima. It never makes it to the second minima. So we have a multiple time scale problem. The time scale, Monte Carlo, it's not quite a time scale because there's no time, but our steps are essentially too short. It needs more steps. It needs more chance to get over to the other minima. How about running other temperatures? What would happen? Take a minute or so. Try running it with different temperatures and see what happens. I'll give you a minute or two. Try running at a different temperature. And see if the mean energy makes it go over. You can post in the Google Doc what temperatures you're seeing, what temperature you need to run for to actually make it to the minima and spend more time there. $20? Yeah, 20. Let's try 20. Ah, there we go. If we look at 20, yeah, it's visiting both sides. Our histogram is, yeah, okay, it's spending a little more time there. Maybe not as much as it should. And our mean energy is about 9. Analytically, it should be about 8.8 or something. Yeah, if we go to 50, it's going to bounce all around. Yeah. And it's visiting everything. Pretty high probability. We don't know what the analytical is, but I bet it's about the same. So if we go up high enough temperature, then it certainly does seem to be doing it. Now, one thing we want to see at low temperature, we know it should spend most of the time in one of the states. If we're running at high temperature, of course, we don't actually get that information. So the simplest thing to do is just run it at high temperature, then we'll visit more points. But it turns out that this is a system, it's pretty easy to visualize. For a real system like a protein, if you try to get from one folded state to another folded state and the temperature is high enough that it unfolds, it unfolds and you never actually see the other low energy state. So this is an example where our system is a little easier than it should be. So just raising the temperature is not going to be sufficient. So let's try some enhanced sampling concepts. So how about this? What if we add a potential that partly cancels the barriers out? If we do that simulation, can we get information back about the original potential? So we're going to define a biased potential. And in this case, it's so simple. Like we know the potential. Let's just completely cancel that out and see if at a low temperature we can actually cross minima. Okay, let's just do it. The complete perfect situation. We know exactly the potential. We exactly cancel it out. And so our biased potential, right? It's just the potential minus the potential is this. Okay, so let's try running it now. Okay, well, now is this particularly typical of what our simulation should look like? Well, we know that it's supposed to actually, at this temperature, it's supposed to spend most of its time between 0 and 1, and it's definitely not doing that. In fact, I think this is a particularly where I'm going to run it again in my case, so it actually goes back and forth a little. That actually would, yeah, okay, yeah. So here it is. It starts out going back and forth, and it just goes out to craziness. So this is clearly not what should be happening. But here's a key. It turns out this is visiting both minima. It's visiting a lot of other places as well, but this is visiting both minima. Can we actually take this information and correct it to get information about both minima? And so I'm going to go back to the slides and cover an important point in enhanced sampling, which is the idea of removing biases. So, a concept of importance sampling can allow us to remove a bias. So let's say I'm interested in calculating a certain ensemble average. I'm interested in calculating the energy at temperature equals 5. And I know that just running a single simulation won't do it. Okay, so now what I do is the thing you always do in math, like this is the greatest mathematical trick that it's used every single time, is you multiply by 1, right? I'm going to multiply by PJ divided by PJ. There we go. This hasn't changed anything, right? I'm just multiplying by 1. Tricky mathematicians always like multiplying by 1, but particular ones. Okay, now what I'm going to do, I'm going to switch these two. Be very careful. It's like a magician there. Keep your eyes on the shell. The I is now on top and the J is on the bottom. Okay, now let's use this concept from Markov chain Monte Carlo integration. Let's say, okay, now I can, if I have this P of J there, I can sample from P of J. And so I can turn this into a sum where now my Xn are sampled from P of J, from this other distribution. However, these this is still equal to the ensemble average over I. So the ensemble average of I is equal to this average of the observable times this ratio of probabilities. So we're sampling from one distribution, we're getting observables from PI. So if I want to get properties of my other distribution, I can take that bias sampling I did that did visit both minima, along with a bunch of other places as well, and multiply it by this ratio, and I should be able to recover the averages. I should be able to recover information about the original potential. So if this ratio is similar in magnitude as Xn varies, we can avoid generating a whole new Monte Carlo chain. We can go backwards and look at it. If it varies too much, it becomes pretty noisy, and we'll see this in a second. So how can we remove this bias? Well, we need to be multiplying each point by this ratio of PI over PJ, which we remember the normalized Boltzmann distribution is going to be the free energy, is going to be, free energy minus energy divided by each other, which is just because we know that exponentials, when we do ratios of exponentials, we get differences in the exponent. E to the beta delta A minus beta delta A minus beta delta U, the difference in the potential energies. So we can calculate this. We can calculate this factor for each observation and get the right averages. So how do we get that difference in free energy, though? We haven't talked about that. Well, we get this. So let's take this formula for the observables that we got, and let's just stick in 1 in each of those for these O. And what we get is this formula. If we divide this, and then we know that this is a constant, it's the same for all the sum, we can multiply both sides for this, and we get this formula for the free energies. If we just add up minus beta difference in potential energy and average that, that will give us e to the minus delta A. So this is known as the Zwanzig formula or exponential averaging. And so finally what we'd get is this. We have here is, we need to be dividing by, so when we do all the division that, we get this. So we can calculate our weight, we get the free energy, and we can plug this in and calculate the weight. So this is a lot of exponents. It's easier if we just go back to the notebook and see how to do this. So let's new share. Let's go back to the notebook. Okay, so we can recall weighting from importance sampling or of this form, where J is the state we care about and the I is the state we're sampling from. For the Boltzmann distribution, it's going to be equal to this. Actually, that J is not there. There we go. It's going to be that. So we need to calculate the energies of our simulation with the potential we care about, not the biased one, the original one. So here our trajectory is this crazy trajectory we took here. We're going to calculate the energies of the new potential at that. Clearly the average of this is not very useful. So let's actually insert. Let's look at let's actually want to look at this. Yeah, so this has some really high energies, which are clearly what we should be doing is seeing a lot of energy at temperature equals 5. We should be seeing a lot of energies around 1, 2, 0. And then clearly these have bad average energies. The average is not useful. So let's calculate the weighted average. So what we need to do, we take this formula, we take all of these energies, divide it by the temperature, right? Because we gotta have a beta there. Oh, see, this is a, I'll have to fix this in the, you definitely remember that beta. So we divide by t, that's the same as multiplying by beta. And then we take the exponential of all these, take the average of this, and then multiply by minus t log, right? So that's what we're doing. We're calculating the free energy. So that's the free energy difference between our biased state and our unbiased state. And then we can calculate the weights of each of those. The weights are just going to be delta free energy. And here the energies here, because the energy of our bias state is 0, right? We're just sampling on this flat potential energy surface. It's just the energies divided by T. One thing you can check about the weights, they should sum to the same number of samples. And wait, what does it mean? Let's see. What did I put the right? It's half that. I'll have to check that later. But let's calculate the weighted average. And so instead of the weighted average being 2, it's about 1.95. It's pretty close. Analytically, it's 1.3. And this is wandering pretty far from that. But it's much closer now. And let's actually see this to understand what's going on. So it's multiplying all these energies by different numbers. Let's look at a histogram of this. So some of them are pretty high. Most of them are quite low. And so how many are above 0.1? So let's actually, we're running a little late on this. So I want to leave time for some other things. So let's see weights less than 0.1. So about 4,000 are less than 1, which is so most of them are less than 1. And if we look at let's look at a histogram of it's plot. Typing too quickly here, so let's make sure we got this right. So weights less than, NP where, that's the thing is. What I'm selecting out the configurations where the weights are big. I want one of the weights, look at where the weights are big. And we see that, what did you hear? Something is up. What am I doing wrong? What went wrong? I'll look on the demo. Most of we want where the weights are high. I'm plotting. What happened with? Did I hit all the energies are behaving correctly? Mean energies. Okay, well, okay. I don't know what happened before. I think I didn't hit all the things. Now everything is behaving correctly. The sum of the weights is correct. The average is 0.96. The histogram is this. Yes. How many are above 0.1? Okay, there we go. I don't know what's happening before. Maybe yours looked correct. Now, what it's doing, it's picking out only the states where the original potential was high, right? This is what's showing up in the average. It's automatically screening out the configurations we sampled that were bad, and we're left with only the configurations that were there in the original state. So that's and so we're getting an average that is very close to the right average, because it's using the fact that all those other energies are really high to just exclude them. So that's what we're getting out. One question to think about is how this might be harder in a multidimensional space. Well, in a multidimensional space, the first thing is you don't know where the minima are. So you can't actually apply a potential that just gets rid of those. So that's the biggest one. And so we'll keep on doing that as we go through. So let's come up with another idea. What if we define some helper potentials that bridge the gap? So this is another method that's frequently used in experimental. So the whole concept of adding a bias to flatten to flatten a potential energy surface out is going to be, we're going to talk about in metadynamics as well. So Omar will talk a lot about strategies for how do you actually find a bias that works. Now, the thing is, our bias is in 1D. The potential energy surface in this case is 1D. But if you have a multidimensional energy surface, that instead of a potential energy, you have to find essentially a free energy surface that cancels out, because it has to take into account all the other dimensions except the one you're searching in. But that's a lot of the ideas, providing this bias, and we'll talk more about collective of variables in that next time. But that's the basic idea here. It's selecting out the it's putting more emphasis on the ones that do matter when you go back. Okay, so here's another idea. So that's one idea, adding a bias to cancel it out that allows you to visit everywhere. Hopefully better than a bias that you just go everywhere. You want to make it a little more sophisticated than that. But the next thing we're going to do is define some helper potentials that bridge the gap between minima. So here I've just got a helper function that's linearly interpolating between two parameters. And what we can do is now we're defining a set of potentials. So each potential, it's going to be a harmonic that harmonic well that goes between the other potentials. So let's plot these as well. So the blue is our original one, and now I have some interpolating potentials that go between them. So what if I could use these other potentials to drag my particle around from well to well? How might that work? Well, in order to do that, we need to do Monte Carlo between states. So now we're not going between x's, we're going between states. So we need a new Monte Carlo step, a state step. So what would that do? Well, first, we need to pick a new state. So what I'm going to do here is going to randomly pick a new state. So we're going to jump to any random state that's not the current state. So I just put in this conditional that it'll keep coming up with a new random number, and it'll accept it as long as it's not like the same one. So there's no point in going from state 1 to 1. You could do other things. For one common thing to do is to say, well, I've got a 50% chance to go up 1 and a 50% chance to go down 1. And that makes sense in a lot of situations, and you'll see some of that in other presentations. So, but for now, we just need something that's isotropic. So if it's even except for my current state, then I to j and j to I will be the same. So that'll work for now. And our new energies will be the energy of the new potential. And so if we switch to another potential and the energy drops, then move, else use that same rule. Notice this line is exactly the same. You're using the same rule. It's just that our old and new are from different potentials. So here's our algorithm now. 50% of the time to a state move, 50% of the time to a coordinate move. So 10,000 steps again, temperature is 5. Now our trajectory is two-dimensional. To describe the state of our system, we have to describe both the location and also the state. Which of the potentials is it in? And now, notice we're using our exact same Monte Carlo step before, because when we're on a fixed potential, we can use the same algorithm. We just need to make sure it knows which potential to use that's passed in, and half the time do a state swap. So let's plot the trajectory. What does it look like? It's moving up and down in state, and it's moving up and down in position. These other potentials are dragging it along. So that's how we've broken kinetics, because but we're still preserving at each of those potentials, we're preserving the right thermodynamics. Let's look at the distributions at each state. So if we do a histogram of where it is, hey, in state 0, it's occupying these with the right probability. And then, it's in these harmonic oscillators the other time. So we're adding these extra states that motion in those states drag it back and forth between the minima. So yeah, so we can look at the potential, just the state. So we can look at the potential of the state, just the state we're interested in. So I'll do this for now. If we go to, are these states physically meaningful? That's a great question. So let's assume that the physics of our original state are meaningful. These other states, all they say is, put it somewhere between the minima. They're not physically meaningful in the sense that they don't have any correspondence to the state we care about, except that they're helping to drag it back and forth between minima. We can look at the potentials 0. We can look at the potential of the states that do happen to be in trajectory I, and we see that, oh yeah, okay. If we look at the average potential, then yeah, it should be about 1.3. It's 1.04. So it is correct. If we look at just the configurations that have that state, they have the correct Boltzmann distribution. How do we apply this if we don't know the energy landscape? Great question. This is a toy problem, right? We'll be talking more about that the rest of the week. This is to just get the concepts down. We say, will they lie on the potential energy surface? Not quite sure what you mean by that, so we might have to come back to that later. Okay, so first of all, here's one thing that we can do. Like, what if there we knew that it was harmonic? What if we didn't know it was harmonic? I'm going to try something different now with idea 3. We may not know enough to morph a potential from one to the other, but what we could do is we could add some potential to localize it. So here what I'm doing, I'm adding essentially umbrella potentials. So what those are for the umbrella potential, I'm going to take the original potential and I'll add a harmonic oscillator. Let's say I don't know anything about the shape of the potential, but I do know where my minima are. So what I can do is I just sort of march between my minima and stick a harmonic oscillator, like go there, now go there, now go there, now go there. So I'm adding to that potential energy surface. So rather than trying to morph it, because usually we can't do that, I can add to it. And so what does that look like now? So this looks a little harder. Like we can, there might be some issues with this right now, but we have, you notice that we do have a minima that we're dragging in from one to the other. If you look over these colors, we can see that it's the system is being dragged from one state to the other state. If we run that though, running the exact same thing, right? I'm running it a little longer so we can see what's going on. Then let's take a look at it now. Plot the trajectory. So this didn't quite do what we wanted it to do. And so what's the issue now? If we look at, it's just staying in the first minima. So is the umbrella sampling right? Yes and no. We are correctly implementing exactly what's going on here, but you notice it's spending less and less time in each of those states. So if it's spending less and less time in each of those states, what does it mean about the free energy of state 4? The free energy of state 4 is much higher than the free energy of state 0. So what's happening with this is that it's actually, if you look at this, once it gets to this state, it's just not going to spend much time in this state because this state is about the same entropy, but a much higher energy. So even adding that harmonic bias in there wasn't quite enough. What we can do is weight these. We can say, you know what? I think it should visit some of these other states more. So what I'm going to do for each of these potentials, I'm going to add now, besides the harmonic oscillator, I'm going to add this extra weight as 2. I'm going to say, hey, state 4, you're not being visited enough. Minus 20. Like I'm going to add an overall energy for that entire state. So I'm going to force it to visit that. Can I do that? Yes. I don't have to visit all my states equally. I can say, I wanted to find a new potential. Visit this one more. So I've got my umbrella samples, the weighted umbrella samples. And what do these look like now? Oh, they're not perfect, but they're more all the same energy. So now if we run that, we can run the weighted umbrellas and plot the trajectory. Okay, it's making it all the way up and down. Now, it's not doing it as much as we'd like. Like we'd have to run really long. But what could we do to improve this? Well, essentially, these weights are saying, add this to the total energy. But if it's a change to all of them, irrespective of the configuration, it's essentially a free energy that we're adding. So what we could do, what could we do? How can we make this better? So one thing we could do is just wiggle with, like, we run it, okay, it doesn't look so good. We need to make some of these other intermediate potentials better, but that doesn't work. That's very unsatisfying. You don't just want to fiddle with lots of variables until it works. So one thing we could do, another way to find the weights is to carry out individual simulations of each of the potentials. This is essentially umbrella sampling. You stick in a localization at each point. So we're going to run each of these umbrella samples. So what I'm going to do is I have it's going to spend 1,000 at each point. It's going to run 1,000 in the first state, 1,000, 1,000, 1,000, and run 1,000 of those across. And we plot that trajectory so you can see. Now, when it's in the middle states, it starts sampling both of those because that middle one sampled both and keep on going up. And so I probably have a couple more minutes than I'd intended to. This is a key point. So let me do this. I might just go a little, 5 minutes long. Sorry. I have to break a little, but this is an important concept that it's a little bit hard, but I think it's pretty key for a lot of the methods. And that is, how do we remove the weights of lots of samples? So we talked about how we can remove one bias, but what if we have multiple biases? Like we get a bunch of bias potentials and there's information in all of them. How can we remove all of those biases? And so what we can do is we can say, actually, we ran all these simulations with different umbrellas. Why don't we just throw them all into one pot and create what we call a mixture distribution? So if we ran simulations with each of these umbrellas, that's the same as running like 20% of these and 20% of these and 20% of these and 20% of these and 20% of these, right? We could think of that as a new distribution rather than individual. Yeah.
Michael, you're not sharing screen right now. So when you're saying these, we can't see.
So I'm so sorry. Thank you. I was getting flustered in this. So I need to do it. I need to actually do the news share. Back to these share. Okay. I'm screen sharing, but it's not actually. There we go. So how to remove multiple biases. So we have several of these umbrella potentials we've done. How do we combine all that information together? How do we can remove the bias from this and from this, but how can we get all the information from all of them together? So what we can do is we can treat this as essentially a single distribution. So we've got a mixture of these 5 distributions. You can think of it as like 20% of the time I sampled from this one, and 20% of the time I sampled from this, 20% of the time of this, 20% of the time of this, right? Like if we treat it as one trajectory, if we lump that all together, we actually did sample all the coordinates. So when I plotted that, that was actually showing a full mixture distribution. Now, if you have different number of samples, then the overall distribution would look like this. There'd be more of these, and so you'd have to weight them with the N1, N2, N3, and you divide it by the total number of samples, so you have an equal, the correct fraction that you put in. So this is called a mixture distribution. So yeah, essentially you're taking all of the samples you put together into a distribution, and you just have to have them normalized correctly. So what we can do to use all the information of the umbrella samples to remove the biases is, this is the formula that you use. And this looks a little confusing for a second. So you notice that this right here, this is just the mixture distribution because it's a weighted fraction of how many came from each distribution times this probability distribution. So, but the probability distribution of each of the individual ones is just the same formula we've been saying, beta free energy minus beta potential energy. That's what's down here in the denominator. So this is just doing the same importance sampling that we did before, where we went for, there we just had one distribution above and one distribution below. We've still got one above and one below, but now the one below, instead of being described by e to the minus beta u, is the sum of all these probability distributions. So if you can do importance sampling for one distribution, you can do it for multiple distributions. And then the observables, you get the same weights out. It's just reweighting from the mixture distribution. How do we find the free energies? Well, we've got this equation is true for each of our individual umbrellas. There's then equations and when unknowns. Technically, it turns out, the free energies differences are the only thing that matters. So you eliminate one of the knowns. One of the equations is dependent on the other. So there's n-1 equations, n-1 unknowns. Once you have those free energies, the formula isn't as simple. It's a set of nonlinear equations, but there's already people that have written code for it. And pi-m bar is actually our implementation of doing this. It shows how to do reweighting for the mixture distribution. There's a lot of things you can use it for: potentials of mean force, solvation for energies, force by a single molecule, experiments even. You can install it through Conda, and it's already installed in here. And so, and this approach has many different variants and many names. You've probably used some variant of this already. Sometimes called the multi-state Bennett acceptance ratio, reduces to WHAM. If you've used WHAM, this is a better way to understand WHAM. Plus WHAM has a lot of histograms that are unnecessary. This sort of boils it down to what it is. It's reweighting for the mixture distribution of what you collected. Turns out to be, if you like probability, it's the maximum likelihood estimate of all the data collected, and it's the lowest variance reweighting estimator as well. So let's go back and apply that, and then we'll wrap it up. I have one example of different temperatures, but you can sort of go through that on your own afterwards. So let's go back to new share. So let's go back to this. So in order to do this, we have to calculate the potential energy of each of the other samples, right? We have a bunch of potential energy differences. I say if you calculate, what I'm doing here is taking all the samples that I've gotten and calculating their energies at each of the other places. And then I have to add up how many samples I have for each of them. And then we stick those energies into pi-m bar, and we get out what the free energies should be. So let's just go back and actually, let's paste this in. Those are what it says the weights should be. So let's go back and plug those in here. Let's plug those in. Let's see. I'm going to show the numbers are right. 0, 1, 2, 3, 4, 5, 8, 9. No, it's 10. Okay. So let's plot these. So they're looking a lot more similar. Some of these have different entropies than others. This one's let's actually see what happens when we run it with these new weights. Plot the trajectory. It's not perfect, but it's a lot better. Fundamentally, the issue is there's this middle state here has a barrier has to cross, but that barrier is now like 15 kBT instead of 60 kBT. So if we run a moderate amount of time, we get sampling from everything. And now if we look at the histograms, it's not perfect. And the reason is that our umbrella samples didn't, in 0, they actually only sampled one of the ends. They didn't sample both of the ends. And so the umbrella sampling was not perfect. But you could actually iteratively stick this into M-bar and go back and get the free energies to be more correct. But this is obviously much better than our initial guess. You can do the same thing with different temperatures. I won't walk through over it quite as much, but you can plot the trajectory with different temperatures, and you can see how, as your different states are different temperatures, it goes back and forth. And now, for running at different temperatures, we can look at the energies as a function. We can use this multi-state reweighting to complete expectations as well. And here's the temperature as at a range of different the temperatures at a range of different, the average energies at a range of different temperatures. So let's go back and compare it analytical. And this is the last thing we'll do. Let's go back and do this at all the different temperatures. Insert sub below and look at if we how these energies are. So at the different temperatures, it's getting most, it's not perfect, but it's getting these averages. Oh, I don't think it's doing it. Oh yeah, there we go. I was looking at the free energies. So the energies there, these. It's getting the average energies pretty much smack dab correct. Because we're doing the reweighting from all the different temperatures. We're sampling all the different temperatures. It's allowing us to visit all the states, and we can reweight and get those right. So that's sort of a taste of how some of these different running a simulation that goes between different temperatures, adding a bias, doing umbrella sampling to reweight and figure out what the free energies of each of the different states are, in a toy model that makes it a little easier to play with. I think we need to take a break so that people are able to head to the rest of the stuff, but I'm happy to answer some questions while we set up for the next one. We might, I don't know, let's say we start at 12 after. Does that sound good? Cool. All right. Can you please talk about how to reasonably reweight it?